well, we call it A-ifcation. I mean, we can solve anything by extending to the, what we call the characteristic extension algebra of the differential equation. The characteristic extension algebra is essentially an algebra with a generator that is a formal mockery of the derivative operator for the differential equation. Everywhere there's a derivative, I have a generator.
Yeah.
And so to each differential equation there corresponds a characteristic algebra. At least if it's a single AODE. And so in this way I can solve any constant coefficient differential equation over an algebra by using the extension algebra and picking off the special functions of the exponential over the characteristic algebra.
So you change the operator for k, which gives you a generator negative j.
Yeah, that's what I mean. That's the condition this one satisfies. K squared is minus j. All that stuff, like the repeated root stuff that you have in differential equations, multiplication by t squared.
Yeah.
All that stuff, you can just see it as there being like a null algebra. Null algebras give you multiplication by t. So in that sense, these null algebras play an important role for the differential equations because there we get multiplication by t in solutions. I just when I saw how this thing worked, I just got chills. I'm like, oh, this is cool. So I was very happy. I gave a talk about this stuff once in one of my interviews in Texas. Where was it? Kingsville? Way down south.
Old school?
I think it might have been Kingsville. It's close to Corpus Christi, but more rural. And after I got talking about this stuff for like an hour, they were like, why isn't this taught everywhere? Like, why isn't this standard material? And to me, that was the highest praise I ever got. Like, because that's how I feel about this stuff, is it's like not that complicated.
No.
But it doesn't have applications. This is why it's not more widely known. In part, is because I can't. You're like, oh well, this is lovely, but what are the applications? I don't know yet, but I know there are applications.
Yeah, but it's just too simple.
There have to be applications to this.
Well, one has an application in complex analysis, doesn't it?
Well, yeah, complex analysis, of course, has been applied places. But there is another. There's something else in complex analysis I haven't told you about yet. There's another problem here that's been partially solved by some students, but I feel like it still hasn't run its course, which is the method of conformal mapping. So in complex, you can solve Laplace's equation over some complicated region. So you know the uxx plus uyy equal to 0 equation. So if you want to solve that subject to certain boundary conditions, you find a map which takes that ugly thing and maps it back to something simple, like perhaps the half plane. So you take your complicated region and you like back to the half plane where you have the boundary conditions put on the real axis. Then there's like this canonical solution that you can just write down to the Laplace equation over here, bam, and then you map it back and you've got your solution in the more complicated region with your funny boundary values. This is the technique of conformal mapping. But what makes conformal mapping work is really just functions and calculus and the fact that the component functions of a complex differentiable function satisfy Laplace's equation.
So if you can find a hyperbolic one?
Then I can do
Then
I can do conformal mapping for the wave equation.
Yeah.
I have no bloody idea what that means. Because boundaries in like the Laplace equation, those are boundaries to physical domains.
Yeah.
Two-dimensional physical domains. Boundaries of a region in space-time, those are weird closed curves that I don't know what they mean. Because like, what's a circle in time-space? not a physical trajectory.
No.
I don't know what it's the boundary of. And yet maybe there's mathematics there that can be done. And my suspicion is that when you find mathematics like that that's so divorced from what is known physically,
Mm-hmm.
you have a good chance, perhaps anywhere, to discover something maybe that's new, physically, that is just sort of on the edge of imagination because the mathematics is. I do feel like there's. That's my most optimistic view is like through that kind of thing maybe you could discover some kind of new solution to the wave equation.
Mm-hmm. But you would solve it in like hyperbolic sense, or like any algebra sense.
Right, yeah, I mean, the problem then becomes how can you take the hyperbolic region and map it to something that you have a known solution in the hyperbolic case?
Yeah, well,
And map
for
it.
H2, you definitely map it to R cross R.
Oh, yeah, well, that's the other thing, is the isomorphism stuff, but here I'm actually just talking about two copies of the hyperbolic plane. But you're right, you could also think about an isomorphism from your hyperbolic space to like the R cross R,
Mm-hmm.
and try to map your solution from R cross R back to there. That is another game you could play. Yeah. But anyway, I will show you the development of this next time we meet. It's got stages. I also spend a fair amount of time talking about like, so we'll look at differential operators, how you can factor differential operators to solve differential equations. I don't think you've seen the annihilator method before, so I'll show you that.
Okay.
So we'll fill in some of the gaps in your differential equations, which are, they're not going to stop, like the gaps I'm talking about, they won't stop you from solving differential equations, but they'll stop you from really appreciating the beauty of differential equations, because there are some very beautiful things in differential equations that are all too often being skipped in the courses. Not just where you are, but everywhere, because there's this dreadful pragmatism, which is draining some of the more pure aspects of courses everywhere. Alright, I think I'm going to turn it off now as the noise from the racetrack is getting a little loud. And I'm also tired. Go figure.